All right, so today we're going to look at logarithmic functions. This takes section 6.3 and 6.4. And I would just want to take a step back to something we'd mentioned earlier. The last meeting, we covered the family of exponential functions. Okay, today we're going to cover the family of logarithmic functions. And for every function in this family, there's a partner over here. These are inverses of each other. Okay, so each function in this family has a twin over here that is its inverse. Okay, so that's why these go together. Okay, so start with a sort of a boring definition. The logarithmic function of base A. So you see the same terminology where, just like exponentials, they're defined by their base, is a function of this form. Log base A of x. So you see the variable here. We call that the argument, right? This is the variable. So again, I'm going to take a step back for this reason. I know students they don't enjoy logarithms. I don't know why. I think maybe the notation is kind of unbecoming. Let's talk about what a logarithm is, and then we'll come back to the aspect of the function. We'll go right with an example. So let's say log base 2 of 8. What is this? What is this thing, this monstrosity? This is a number. Okay, this is a very unattractive way to represent some number, but what number is this? Well, a log, I'm going to abbreviate right here. A logarithm is an exponent. That when put on the base, right, we put exponents on bases, right? The base, so this is a base 2. Yields what we call the argument. So what do I have to put on 2, question mark, to get 8? 3, right? So this number is 3. That exponent that needs to be put on 2 to achieve 8 is 3. Okay, so if you kind of say that to yourself, if you have to evaluate these, what exponent do I need to put on 2 to get 8? Whatever the numbers are, I think it'll help. I just want to run through a couple examples and a few sort of special cases that sometimes freak students out. The good news is, without calculators, we're very limited into the ones that you can ask and be practical. But let's go with 381. All right, what exponent do I have to put on 3 to get 81? Well, 3 times 3 is 9, times 3 is 27. Another one, 4 of them give you 81. Okay. What exponent do I need to put on base 4 to get 16? 4 squared is 16. Okay, so you see how this works. It's not a big deal. Hopefully, a couple special cases. How do you get to 1? What do I put on 5 to get a 1? 0, right? Anything to the 0th power is equal to 1. So that's, let's do this. So this might look a little strange. Right? What do I have to put on 2 to get a half? And you might say, well, that doesn't even seem reasonable, right? But what happens when you have a negative exponent? Right? You flip. You move this to the denominator. So this would be 1 over 2 to the 1. Right? To the 1. I won't write the 1. So the exponent needed here is negative 1. Okay, remember, if you see negative, if you have negative logarithms, you're doing the whole numerator denominator thing. Okay, so evaluating them shouldn't be difficult. So just add this note. This is sort of combining the definition and what we just discussed. So, and this might seem like a little overkill, but given log base a of x equals whatever this number happens to be y, then of course the base to the exponent is the argument. Okay, so this is sort of a mathematical statement of what I had in plain English on the last page. Okay, so let's see. Let's put these here. This is important material right here. Logarithms. It's a weird word to spell. Okay, we usually teach these in pre-calc, but these are important, so I'm going to put them here. Another thing, just to note, well, I'll come back to that. Let me relax here. Okay. So I have log to some base of the argument happens to be a product. Right? Two things multiplied. And these are all rooted in the properties of exponents. Right? What happens when you multiply two things? What do you do with their exponents? You add them. So I'm not going to do a proof, but that property leads to this property. So the logarithm of a product can be written as a sum of two logarithms. And notice the base has to be the same throughout. Otherwise, it's nonsense. Okay, and likewise, what happens when you got two things, common base with exponents, and you divide? You subtract them, right? Okay? And then last but not least, I have an exponent within the argument. What this allows me to do is pull that exponent out as a coefficient. So a couple things. These are equations, essentially, right? So that means these are used both ways. You might have a situation, you're going to see it in the next section, where I'm going to have a logarithm, and I might want to break it up. I might want to break it up into multiple, simpler logarithms. And I might have a situation where I have a whole mess of them, and I want to just have one, because a lot of times one thing looks better than five things. Okay, so keep that in mind. These are used both directions. Another comment I want to make is this property is very powerful for this reason. You might have seen this formula. Let me see, future value. If you haven't, no big deal. This is a finance. I don't even know if I'm right yet. P plus I N T. This is a future value of money formula. And you guys deal with formulas and you solve for the different variables. You push stuff around, in physics and whatnot. If I want to solve this equation for one of these two variables in the exponent, I'm stuck. These guys are stuck up here. So the proper way that you would do this, and I won't bore you with it right now, maybe I'll bore you with it later, we would take a log, and this isn't exactly what you would do, of each side, right, all this, and then this property would allow those things to be pulled down. And now I can manipulate really nice and easy. Okay, so these are very useful. I'm just going to do a couple examples of what's in the homework. It's pretty straightforward, but just so you can see them. I'm going to say we're going to go both directions. Expand. So I'm going to expand, and the base is really irrelevant. I'll just make it 2 since it's easier to write. Let's say square root x plus 1 over x plus 2. Okay, so first thing I'm going to recognize is this hat is not my friend. Okay, so the first thing I want to do, I'm going to pull that exponent out. And what's left in the argument is a quotient. And I can split that by subtraction. Keep in mind this half is attached to this logarithm. It needs to be attached to both, or I can just use parentheses. Minus. Okay, why would you want to do that? Well, maybe you wouldn't, but maybe you would. Okay, so we can, and these things you can make them so they split up into 15 different ones, but those 3 rules are in play. And like I said, you might want to go the other way. What's the opposite of expand? Condense. Express as a single log. So maybe something like this. Let's see. Give myself some room here. Log base 2 of 4 plus log base 2 of a minus 1/3 log base 2. Oh, I want to mention something. You might say, why didn't you do anything with that? Come here. There's no property for this. There's no, if the log of a sum is the log of a sum, end of story. Okay, so don't make up your own rules. All right, let's do a couple things at once here. I'm going to combine these two, right? I'm going to combine these two into a product. Log base 2 now of 4 times a. And I'm going to throw this third up in here as an exponent. Okay? And now I have 2. I have 2 via subtraction. I'm going to combine them as a quotient. 4a over, this could be written as a cube root. In fact, why don't we do that? Okay? So you'll be asked to do that. Memorize those rules. Okay, now I want to go back to the conversation we had where we had an exponential family and what do we call that? A logarithmic family, and how they were inverses of each other. So the following statements are rooted in the inverse function conversation, and the notation is a little messy, but don't let it bother you. So f of x equals log base a of x, so this function is defined by whatever a is always the inverse function of, I'm going to write this as g, I could write it as f inverse, but I'm stating it's an inverse of a to the x. Okay, so you go back to this, beauty. Which pairs pair up? The pairs that have matching bases. Okay, log base a matches up with the exponential of base a. Okay, and then the reason I say that is because I'm going to write, just as a quick reminder, don't write this down because you already have it down. How do you know you have 2 functions as inverses? When you compose them, you get x. Right? So remember that from last week. So in other words, if I compose these, which is a sight to see, they're going to result in x. The point being, okay, let's put this one in this one, f of g. Okay, well that looks like a to the log base a of x. So this is a to the exponent that I need to put on a to get x. And then likewise, if I go the other direction, log base a of x is of course x again. And why is that important? Because when you have inverse functions, they can undo each other, right? Go back to algebra 1, minus whatever, and you got to solve this. What do? You do this kind of thing. You're doing sort of the opposite, right? You do that, right? That's going way back. It's similar. Like if I have 2 to the x, equals a bunch of mess right here. Well, if I take the log base 2 of each side, I get cancellation over here, right? And so you think about that, right? Applying one of these to the other one cancels them out, and you get x. Okay, but that's by definition. This is by definition of inverse functions. Okay. Now, going back to I don't remember what day, Wednesday, whatever, Friday. We talked about general exponentials, and we just spent the last 17 minutes talking about general logs. And then after the whole conversation with exponentials, I got fixated on one specific one. That was e to the x, base e. And we're going to do the same thing here. Right? The logarithmic function of interest is the one that matches up with this. So of course that would be this. Now here's the thing. Let me write this out. So this is the natural. You'll hear the people say natural log. That's the natural logarithmic function. So there's infinitely many, elements in each of these sets, but we focus in on these two really. Is of course this. Now here's the thing. I think you probably know where this is headed. To make us irritable, rather than just use this standard notation that we've been using, they decided they have to have a special notation. So you could write this, but nobody does. Instead, they use this. This is this. This is a log base e. We call it the natural log. So what I'm going to do is, this is nothing new. This is all the things from the last few pages, but I'm just now going to represent it with this notation rather than what we've been writing, for the last 20 minutes, which is the log notation. So again, the definition of a logarithm, if ln x, what number is that again? This is what I have to put on e to get x. So if this is some value, this is if and only if. This is some value, this is the exponent, I put on e to get x. And going back to the definition of inverses, if I take the ln of the e to the x, I get cancellation. If I have e to the ln of x, I get cancellation. Commit these to memory. It's hot in here. Oof. All right, what exponent do I put on e to get e? 1. What exponent do I put on e to get 1? E to the 0, right? So these come up a lot. You know, if we're not using a calculator, I can't ask you that, right? So you'll see these like in definite integrals and things, because they're really the only ones we can really ask about. Okay? I'm gonna get a drink here. We're gonna have some graphs. And let me just get a sip of drink here. Okay, remember that something I mentioned is you have good understanding of the properties of a function if you have knowledge of its graph. We talked about e to the x, which I'll just kind of put in the corner here. You already have this. Right? That's e to the x. So if you know that picture, you know a lot of the properties. So we're going to talk about now similar idea. Properties. Properties, is that spelled right? Properties. Doesn't look right. Properties of the ln function. And these would hold for any log of base greater than 1. As we list them, we're going to build a graph. Okay, so f of 1. Right, what's happening at 1? But let's do this as well. Let's label this. Well, what exponent do I put on e to get 1? E to the 0 is 1. So f of 1 is 0. So this is the root at 1. That's not what I want. But what exponent do I put on e to get 0? Well, it's not 0. 0 gives 1. And you start thinking there's got to be something. There's no number I can put as an exponent to get 0. So this is not equal to undefined. This is undefined. So this would be the case. It's undefined for any negative value as well. So we'll come to that right now, actually. So what does that mean? Well, I got to start to the right of 0. So the domain, and this is important, the domain of the ln function is positive values only. From the axis to the left, nothing happens. Range, all real numbers. Okay. So think about the domain and range. Remember that inverse functions flip-flop domains and ranges. This was the domain of the exponential. This was the range of the exponential. So these fit perfectly. What about limiting behavior? To the right. As I go to the right, I kind of drew this like it levels off. It does not. Okay, this goes unbounded. So as x goes to infinity, the function goes to infinity. And I can't go to negative infinity because I can't go past the axis. So I'm going to say, what is the limit as we approach this vertical asymptote? Right? This is a vertical asymptote. Whoop. This baby goes all the way down. Okay, so as we approach 0, we go to negative infinity. So again, if you know this image, you know all this stuff. All right? And this is important stuff. This comes up. I don't want to downplay it. How we making out here?